Hello, my name is Isaias. I am a PhD student at the University of Campinas, in Brazil. Today, I am going to talk about how we rely on quality to evaluate approximate computing designs, and why this may not be such a good idea. First, let's look back and see why we design approximate systems in the first place. There are applications where accuracy is not a strict requirement. Let's say we are deploying a sort of a monitor system for cattle in a farm. We can take the most accurately perfect path that would take the best possible images for later image classification. Or we can use a less reliable but also less expensive channel that allows for some noise or approximation to be present in the images. At the end of the day, both ways could act the same way for the common goal of finding cattle, but the approximate one is more efficient in some aspect, usually for costing less energy. But how do we evaluate what is a good approximation and what isn't? Well, first, we seem to just forget about what the approximate outputs were being used for and the context from which they were processed, and focus just on the approximation injection itself. Thus, we compare the approximate and the accurate outputs using a metric that could well be defined as an accuracy metric, even though the first assumption was that we do not need accuracy. But here, we conveniently rename it as a quality metric. Then, we compute these quality metrics and compare them against the energy cost to produce the results, showing that there exists a trade-off between quality and energy, and implicitly inferring that there is a point of operation at which quality is good enough and energy is low enough to maximize efficiency. From this point on, we start comparing applications and approximations against each other, showing how they can save more or less energy and still meet the same quality criteria. Finally, this brought up intelligent systems designed to search for the highest energy savings that can still meet the quality criteria. At the end of the day, the evaluation relies on a magic value of a quality threshold that would determine when the approximation is good enough. From experience, it is natural that higher values in the order of 90-something% are easily accepted, while one trying to lower these bounds would have a lot of explaining to do. But what does, or doesn't, this quality threshold mean? Here, we artificially modified our baseline image in 5 different ways. Since our quality metric would essentially tell how similar two images are, we can easily classify them manually in similar or different. Ideally, our quality threshold would split the set here, where similar images are good enough and lead to efficient approximate computation, and different ones are not good enough and should be discarded. However, if we actually compute the quality metrics and order the images from higher to lower values, this is what happens. Here, there is no single quality threshold that can reliably split the set of images. Any choice would whether leave useful images behind or bring useless ones in. If the quality evaluation based on thresholds is flawed, then what we propose instead? We take a step back and reconsider the fill scenario. Our application had an input that was common to two paths that could be subjected to approximation. We have been evaluating the approximation based on its direct output. But what really matters is not how accurate the approximate output is, but instead what difference it makes on the final outcome of the application. If the final evaluation is the same for the same input, then the approximation is just acceptable. Then, this is our acceptability metric. To put the idea to test, we experimented with 3 different scenarios. Each scenario is a target application, and the approximation comes from its memory accesses that are subject to noise. All experiments were repeated at various meaningful error rates. In the first scenario, we employ image classification on more than 13,000 images from the ImageNet dataset. The approximation was injected in a JPEG compression step, which, in this first example, completely messed up with the luminance values during compression. This visually destroyed the image. Our quality metric, the structural similarity index, captured this difference with a high penalty, evaluating quality at only 20%. However, the distinct ornament in the ceiling, the borders of the building, and the lack of other relevant elements in the scene were probably enough for ResNet 50 to still tell us it is a church, as its top 1 classification, despite the impact on confidence. In another example, the approximation caused minimum noise and the image is visually indistinguishable. However, it came from a much less favorable input, as noticeable from the classification confidence, where even a small amount of noise could cause an incorrect classification. This shows that the input, which is context, matters. Our second scenario is license plate recognition. We read license plates from almost 2,500 pictures. The approximation was injected in the data transfer, modeling an unreliable channel, and the quality metric is also the structural similarity index of the images. Here, for example, we can see how some noise in the top of the image can strongly hurt the quality metric, but has no effect on the final reading of the plate. On the other hand, the recognition software itself is not very resilient, and even minor changes can lead to an incorrect reading. This shows that what the approximate outputs are used for, which is also context, matters. The final scenario is pitch recognition. We use the fast Fourier transform to recognize the pitch of more than 2,500 instrument samples. Quality is the complement of the mean absolute percentage error for each of the complex values in the frequency domain. Here, the pitch is the dominant frequency in the spectrum. This first example is a cello playing G2, which sounds like this. The approximation truncated most of the samples in the frequency domain, which severely hurts the quality metric. However, the 98 Hz peak is still there, which leads to a correct recognition of pitch. On the other hand, in this oboe playing C6, the frequency spectrum looks all messed up. However, these are only 40 well-spaced outliers in more than 60,000 samples, which almost do not affect the quality metric. Any one of these outliers can displace the original peak from 1045 Hz, which lead to the recognition as a E-flat 5 instead of the original C6. These examples show that context, such as the input, some application characteristics, and events that happen by total chance, can strongly affect the outcome and may not be captured by the quality metrics. But how much does it matter? Let's see some statistical evidence. These plots show, for each application, how many of the results in the y-axis that met a given quality threshold but were lower than the next one on the x-axis are deemed acceptable by our acceptability metrics. Note that a lot of the bad results in red, which are the ones with lower than 90% quality, are actually pretty acceptable, while many of the better in yellow should be discarded. Even the results that achieve the extra conservative 99% threshold can be not acceptable in green, especially for a less resilient application such as license plate recognition. Thus, whichever is the threshold, some of the useful or useless results are incorrectly classified by the quality evaluation. These plots show how many are incorrect in the x-axis for each quality requirement in the y-axis. False negatives in the left-hand side are results that are useful but do not meet the quality requirement, while false positives in the right-hand side are results that meet the quality but should be discarded anyway. Both types of incorrect classifications are bad, but they grow in opposite directions, which means we cannot minimize them both at the same time. In our evaluation, these results are more than 5% in yellow or more than 10% in red for any of the quality thresholds. These results may suggest that we could still get away with quality-only evaluation if we tolerated up to 10% false results and used lower thresholds, such as 80% in more resilient applications. But let's take a look at the bigger picture. These plots show how many of the whole set of possible approximate results in the y-axis are acceptable in green or unacceptable in red as captured by the quality thresholds in the x-axis. In our scenarios, the choice for a conservative quality threshold will leave behind up to 13% of the results that were to be useful. Each and every one of these are opportunities that we hadn't missed to improve the energy efficiency of the overall system. However, relaxing the quality requirements with no regards to acceptability can lead to up to 35% of useless results. These all represent energy and resources that go to waste, let alone any consequence on the overall reliability of the final system. Thus, in this work, we've shown that quality-only evaluation of approximate systems, as we have been doing, is an easy and flexible method but cannot capture the usefulness of the results. This may well be because we are using the wrong metrics, and we need better ones. They are not developed for these scenarios after all. They rely on accuracy for systems where accuracy is relaxed, but they are the metrics that we have. While a more representative quality evaluation can be developed, it is important to show how useful the results are instead of just how accurate they are. To this end, the whole context of the application matters and is determinant for the overall evaluation. In our demonstration, an acceptability analysis allows up to 20% more valid results that would not be considered useful by conservative quality thresholds. Our next steps are to extend this acceptability analysis to other scenarios and different types of approximation and other applications. This should allow the design of automated systems that are designed to deliver acceptable results instead of to meet accuracy requirements. The experiments in this work were based on XPike, our in-house simulator for approximate computing, and AXRun, our memory interface that allows for reliable data access into approximate memories. The overall motivation came from the design of SmartApprox, an automated system that finds an efficient point of approximate operation based on common characteristics between applications. Check them out at varc.github.io. That's it for today. Thank you.